Hello, and welcome to this Aerospace Testing International webinar in association with VTI Instruments and AMETEK. You're very welcome. It's good to see people joining. You may be wondering why I'm the only person here on screen. That's because, never fear, we do have Nathan Henderson is here, but he is not on camera. My name is Tom Stone. I'm editorial director of Aerospace Testing International. So I'm the webinar host today, but I will be handing over very shortly to Nathan. Nathan Henderson is a senior applications engineer with VTI Instruments, and for the last he's been with the company for 10 years, and he's got previous military training in aircraft, avionics, radio, and radar. So he will be presenting. Nathan, are you there?
I am here, yes, thanks, Tom.
Loud and clear, fantastic. So we'll hand over to Nathan in a moment, and he will be presenting with some slides. So there'll be plenty to look at. If you're joining and using this platform for the first time, I can tell you that you should, on the right-hand side, see the Q&A panel. You can ask a question there at any point during the webinar. It won't be published immediately, but at the end of Nathan's presentation, we'll get to a Q&A session, and during that session, I will publish any of the questions that we answer, and so feel free to drop a question in there at any point during the session. So I think that's all we need to know. So without further ado, Nathan, I'll hand over to you. Let's see if we can get these slides up.
Let's go. There we are. Thank you for the intro, Tom. That's great. So as Tom says, I am the Senior Applications Engineer for VTI Instruments. We're going to take us through a little presentation that we've put together today talking about Driverless RESTful HTTP, a method of controlling your hardware without needing drivers. So I've got a little agenda to work our way through. We'll quickly cover who we are as VTI Instruments. We'll give a quick introduction to test system development. I'll briefly go over the history of programming as well, because it kind of leads on to where we're trying to get with this, along with certain standards such as hardware communication. We'll look at the actual task of programming your data acquisition hardware, and then how we approach doing that without needing drivers. And then a little extra that I've put on the end of here, which is Node-RED, and we'll discover some more about that and how that can really help you along the way. And then finally, I've got a conclusion to run through, and then after that we have some Q&A time as well, which hopefully is going to create some questions as we work our way through. So, VTI Instruments, we are a USA-based company, or to be more specific, Southern California-based data acquisition and functional test company. We've been supplying aerospace and defense aerospace industry for more than 25 years, but that's not our only market. I mean, we supply anything from white goods testing through to space projects. We, in 2003, acquired a large portion of what was then Agilent, or now Keysight's, structural test business or mechanical test business, and we've been slowly growing that since then. So everything to do with strain gauges, NVH, and vibration, anything along those lines, we've added to what we originally bought and developed quite a portfolio for it. VTI Instruments, for most of our history, our instrumentation has always been Ethernet based. In fact, we conform to the LXI standard, and that was a standard that we co-founded with Agilent, as they were at the time, and so we are certainly a leader in that standard. And I'll cover that a little bit more as we go along, because it's quite relevant to what we're trying to do here with driverless. VTI Instruments is now part of AMETEK, and to be precise, the AMETEK Programmable Power business unit. AMETEK has a global presence, and it certainly helps us be more of a global supplier as well. So what we're going to be talking about here is test systems, and when looking to build a test system or to contract a system integrator to build you a test system, and certainly when it comes to aerospace testing and that sort of thing, we're looking at larger test objects such as fuselages and wings and things like that. Although what I'm talking about is also relevant to smaller scale testing as well. Usually a system spec is developed for your test system, and it normally comprises of things like what sort of data acquisition speed you want, the accuracy that you're looking for, your resolution, channel count, etc. And those are usually the basic requirements that are put into the first initial draft of a test system. And then it falls to the finer details, and we're talking communication standards, programming environments, operating systems. Do you want your test system to be future scalable? Or do you want a distributed test system? And if you ignore these, what I'm going to call secondary requirements, it can add massive cost and delay to building your complete test system. And the little diagram I've got down the bottom here, basically, there's the test item that you'll all be the experts of, and the sensors that you know what sensors you want and where you need to place them. Then traditionally there is a large amount of extra long sensor analog cable runs from your sensor back through to your centralized data acquisition system. And that data acquisition system may have various different types of communication methods back to a central processing PC that's going to process your data and capture it and everything else. The setup is somewhat time consuming and an expensive approach if you're looking at large scale data acquisition. So what we want to do as we work our way through this presentation is break this down a little and explain how we can do this, let's say, a more efficient way, and certainly in a way that makes maintenance and future expansion a lot easier. Then the next thing that I want to sort of touch on as well, and that's turnkey solutions, turnkey systems. So most manufacturers will offer a turnkey solution for their hardware. So you get the hardware and the software bespoke to that hardware as a turnkey system. The issue with that, and it's certainly a time saver for sure, but the issue here is that if you're looking to test something specific and you're going to end up wanting a bespoke test system, it's often the case that a single vendor is not going to be able to supply you all the hardware that you require to complete every part of your test into one system. And the example I've got down here, where we've got an accelerometer acquisition system and also an industrial control and acquisition system, you're not going to find a single turnkey software solution that's going to combine both of those and give you what you require. So what I'm getting at here, there comes a point where there is a necessity to get a software written or to write your own software to create your own test system. And it's these kind of tests which is where we're particularly interested in giving you some time saving. So we've spoken about the greater test system and understanding things like your data acquisition speed and channel count, etc. And then after selecting all the hardware, and it's important to select the hardware that all complies to the same industry standards. It just means that your system is going to be a lot more compatible within itself. And a continuation from this is selecting the right standard for your application. And as we'll work our way through this, looking for things such as popularity of the chosen industry standard is important, because you want the most amount of available hardware to fit within your system, or give yourself the largest options in the way of what you can select to build your test system. And also think about test distribution, along with speed and other added features that are beneficial to your test. Selecting a standard that enables you to decentralize your test is certainly important for large scale, and very much so applicable to small scale testing as well. And it'll greatly reduce, as I was speaking about earlier, the cost of transducer cable runs and things like this, and ending up with weak or noisy signals. The quicker you can get your data or your transducer data converted into digital data, the less risk you run of getting noise or weak signals or other such issues. And I've listed shown some logos below of some of the standards. Now, some you may be familiar with, things like the old VXI bus standard and PXI standards, which are a card slot system. Say you buy a chassis and you add cards to that. Those are hardware standards. Above that, we've got LXI, which is a communication standard for instrumentation. And then other things that you'll recognize on here, such as the Windows logo and Linux logo. The IVI Foundation goes hand in hand with LXI. And then there's a couple that are perhaps not so expected on here, things like Amazon Web Services and Google Cloud. And I'll explain those a little bit more as we work our way through that, but they become quite relevant to this driverless approach that we're going to look at. So if we just do a brief history of programming, and I'll skip through this, but basically, given that our bespoke test system is going to require software, it's useful to understand what is available and why. And to start off with, what is a programming language? And programming languages were developed to move away from machine code. And the first programming languages date right back to 1949, when assembly language was created. So rather than controlling a processor via sending it a stream of zeros and ones to set and get data from registers, etc., machine code or assembly language was created to give a slightly higher level control over what you were doing. And since that point, moving forwards, we've seen many different software applications appearing that each one brings with it the ability to make that programming experience a little more human language based, a little easier, a little clearer, a little bit more intuitive. So I've got a timeline listed along the bottom of this slide. I've also kind of changed the markers for them. So those in the larger circles are probably more relevant to where we are today than those in the smaller circles. And I've got a few along here. The big ones that really jump out and should jump out to anybody developing a test system are things like LabVIEW, which was introduced in 1986. LabVIEW was a big breakaway from all of the other programming language types in that it was not a case of writing lines of code. LabVIEW was a drag and drop, very graphical block diagram way of programming, and it still exists till today and is certainly one of the biggest players in test and measurement software development. We have a few others along here. Python, which has grown to be quite the programming language these days. HTML, which came with the introduction of the Ethernet and the internet as we know it today. And right at the end, I've got one that not many people are quite familiar with at the moment, which is Node-RED. And again, we'll cover that as we work our way through. But the point to take away from this slide is with every development, it's made creating your applications, writing your programs more intuitive, quicker, easier. And while we think about programming languages, let's look at popularity as well. And the reason you want to do this, the more popular your programming language, the more resource you have. So that's the more programmers that you'll be able to hire or make use of for writing your application. And also, the more popular the programming language, the more web resource you'll get for it, the more examples, the more tools, the add-on modules, everything else that goes with it. And to that end, there is a website that helps you to select this, and it's the TIOBE website, and I'll put the web link here on the slide. And they create every month a rundown of the top 100 programming languages. And I've got the results here for June 2022. And as you'll see, number one on the programming languages list, the global most popular, is Python. So it's certainly a language worth looking at if you need to develop a test system, because you're going to get the most amount of programmers. It's open source. There's the most web resource, and it generally, going with a popular language will really help you develop your test system. Off the bottom of this list, we have still on there Fortran which was developed in 1957. It's still there in 18th. MATLAB closely on behind in 20th. Interestingly, and certainly for those in test and measurement, is to find out that LabVIEW is down in 49th position. It is the 49th most popular programming language, which in test and measurement, you would think that it was the number one. But globally, it's way down. So you would find far more Python programmers than you would find LabVIEW programmers, as an example. And then we jump to hardware communication standards as well, because this is something else important. If you're building a test system, you need to be able to communicate with your data acquisition and anything that's putting excitation into your system, and you need to be able to communicate with it. And there's been a few standards that have come along since the 1960s, and they're all still here to this day, interestingly. Everything from RS-232, the original COM port, and the LPT ports that followed with that as well, launched back in 1960, right up to the latest USB version 4 now, as it is. And I've put on this slide some data on max data rate and max cable length, but that goes hand in hand. The longer the cable, the lower the data rate is generally how it works. And you'll see on here that Ethernet is quite an old standard. It's been around since 1980, and it's still here to this day. And its popularity has grown and grown as it goes. USB these days, as I say, USB version 4 is now one of the same communication standards as the Thunderbolt connection that you now see. So Thunderbolt and USB are very much the same thing these days. But at least you can see the standards that are here, and roughly their data rates and cable lengths that you can use. And as I said, of all those standards that we previously listed, Ethernet is by far the most common. It has the largest global acceptance, and it does that by how it was set up, and the fact that it offers the greatest expansion and decentralized distribution or distributed options for any test system. And whilst Ethernet in its own isn't necessarily the most time deterministic or best standard perhaps to use, or wouldn't appear to be the best standard to use for this sort of thing, there have been many standards developed along the way that have been added to Ethernet or local area networks to make it a great candidate for test and measurement. Things such as LXI, which has added a layer of instrument detection, virtual trigger bus lines, common programming APIs, and all this sort of thing, help bring things together. To add time stamping, we have IEEE 1588, or PTP as it's better known. And then there are other things such as EtherCAT that's been developed, which makes Ethernet time deterministic as well. So you end up with a test system that is not only distributable, but you can also get your data not only quickly, but you can get it in a deterministic correct order. So you not only know what happened, but when, and that's always very important. And if we pull this all together in one slide, then we look at the actual task of programming your test system. And in the 1990s, it was a case of using either Skippy, which was standard commands for programmable instruments, which was a form of driverless control, or failing that, then there was always the option to get proprietary drivers. And you bought the driver or software development pack from the hardware vendor and developed your system, usually or almost exclusively in a Microsoft operating system or on a Microsoft operating system. And you had to buy your programming language to go with that. And I remember when those sort of programming languages came with a massive price tag. And so the whole task of creating your own application was an expensive one, and also quite a complex task as well. Jump forwards to the 2000s, and many industry standards have been introduced to create drivers that all conform to the same standard. And so now when you started buying hardware from different from different hardware manufacturers, at least you had the same basic command set between each of those hardwares to add to your system and make your system development a bit easier. Since then, there's been a massive growth in the popularity of Linux OS, and so many of the manufacturers who offered traditional Windows APIs or software development kits, drivers, etc., also ported this to Linux. And now you could write your application to work on Windows, or you could write it to work on Linux. So you had now an option on which OS. Things have changed a lot now, and we look at the 2020s, and the thing you hear all the time is IoT, Internet of Things. And it's very much taken the lead, and with that comes the need for driverless control, which is where we're heading today. So therefore, not only does an application need to be OS and programming language independent, it also needs to be processor independent. So you're not locked to that standard Intel or AMD processor. You can use an ARM processor or anything else like that. And that's where driverless really comes into its own. You are completely free to what system and how you control that hardware. So now we start looking at controlling an entire test system or parts of a test system with single board computers. And I'm talking things like Raspberry Pis, Beagle boards, and custom-built ARM-based single board PCs. And they have really taken over from what was once the rack-mounted industrial PC that we always used to see. So looking at IoT a little bit more, it's the name that's generally given to devices with sensors or that exchange data and connect to the internet or to a local area network. This, by definition, means that every LXI-based hardware data acquisition or signal generator, whatever it may happen to be, anything LXI test and measurement based, falls into this IoT category. However, unlike your normal gadget-based IoT, this sort of hardware, the LXI-based hardware, adds a much improved sensor accuracy, speed, external control than you would find on standard and low-cost home automation type devices. And while IoT is generally associated with smart home, smartphone, smart speaker type devices, the infrastructure and the idea behind it is very strong, and it really should be given some serious consideration when developing a test system for an industrial application. IoT brings with it many time-saving methods and a massive support community that help reduce test system development time. And that's the key. It is a time saver, and it's going to make it easier to develop test systems. But before we can do that, there seems to be a mindset change that's needed in order to adopt IoT into industry. And there's a few things to look at on this. I mean, it's estimated today that over 80% of all new electronic devices will be IoT. So IoT has the greatest potential to advance and improve our life with smart comms and great interconnectability. And we look at mobile phones. 20 years ago, a mobile phone had a camera, it had a color screen, it had a keyboard, it had a microphone and a speaker. And all we ever done was send text messages and call people. And then someone added an operating system to that phone. And because there was now an operating system on there, it opened it up to developers to create apps for that phone that used any of those individual hardware components to convert it into something else or to give you extra control or functionality. And with that, the smartphone was born. And IoT is going to do the same thing. Same goes with TVs. You now get most TVs are smart TVs. They have a processor built in. They have the ability to add apps and do different things and connect to the internet. But at the moment, IoT is still seen as a nice-to-have gadget, shallow and consumeristic. But like software has done in the past, IoT will continue and consume the world in many network-connected data acquisition and transmission devices. And after all, the more data you gather and the more control you have, the better your understanding of the item under test or whatever you have in production. there's been a few names given to this. Generally, it's called IIoT, which is Industrial Internet of Things. In Germany, they call it Industry 4.0, and that's quite an interesting idea. And I've put it together as a little timeline at the bottom of this slide. So you've got Industry 1.0, which was the original mechanical production line using either steam, wind, or water power to produce whatever it was that you were trying to create. Industry 2.0 saw the introduction of mass production, assembly lines, and factories using electrical power to enable them to do this. Industry 3.0 was computer automated production and data acquisition, and it was all a centralized system with a control room and everything else that you see in the little image there. And then we move on to Industry 4.0, which is the cyber-physical automated system and distributed data reporting. And it enables you to open out what you were originally doing as a central location and distribute that data to anywhere that requires it instantly. So the VTI approach to driverless instruments, and this is where it gets interesting. This is a bit of a page for this one, so we'll go through this quickly and then I'll explain a little more afterwards. IoT, because of its multi-platform adaptation, is by default driverless. We've already discussed this. And at VTI Instruments, to go driverless, we chose to use representational state transfer, or REST, as it's short for. It's a standard that's transmitted over HTTP, and the reason we selected this, and there's many reasons, and these include things such as the RESTful HTTP is the de facto standard for accessing resource and communicating over the web. You may not realize it, but you use it every time you go on the internet. And then the web as we know it today was and still is heavily influenced by RESTful HTTP. It makes use of HTTP verbs that most of us should know, such as get, post, put, delete, etc. And even if you don't know what they are, their names are pretty clear and self-explanatory. And HTTP is the foundation for data communication on the internet since 1990. It was developed as a language for displaying text, images, forms, etc. on a web browser. RESTful APIs typically use JavaScript object notation, or JSON, as the data interchange format. That's the way that we send a list of configuration data, or we report back a instrument's configuration. And it's a very, let's say, high-level English-looking language that you can send back and forth and read data on. It's been adopted as the standard because it is more compact, smaller in size, compared to the original XML type. And also because of that, it can be read and used a lot faster than XML. But RESTful HTTP is very flexible, so you can modify that, meaning that you can send data, receive data in JSON, XML, and so on. And we'll look at that as we work our way through. So how does this look as an image? Let's put this a different way. You can use any processor type, Intel-based, ARM-based, or whatever it happens to be. And you can run that on any operating system, iOS, Android, Linux, Windows, whatever it is. Or you can use any web browser available today. And you use that to send this JSON data with a get, post, put, delete command over your local area network using HTTP to your instrument or server. It responds to that and then sends you the data back as a get, post, put, delete, and back to your web browser or back to your application under whatever operating system or whatever processor type. And it's as simple as that. To put that into more of a block diagram below, we have a green box with clients. So and your client can be anything, a web browser, a JavaScript app, Python app, any other programming language that you want to create it in. It can be another IoT device. It could be Node-RED. And all it's doing is sending, in this example that I've got here, a get command to a directory on a website address to retrieve a serial number. The server, which could be a physical device, test instrument, it could be an application on another PC, it could be a web location, it could be a LAN location, receives that information, responds to it, and sends it back as a JSON file to the client, and so on and so forth. And it really is as basic as that. How does that look? And I've used a VTI Instruments device here just to show how this works. So all you are doing on this web browser here, you call the IP address of the device. And in this case, I've used a PXIe type setup here. So you tell it which card slot number it is. And you leave it open at that, and it'll give you a list of what your next directory can be. Each one of those is the next page along on this website. And then the same on the other side here. Once you've drilled this down to wherever you want to be, digitize a measurement, there are your final commands that you can either get, put, post to, and get your data back. So we are quite simply calling a directory within a website page. So other advantages to using RESTful HTTP, it means that it is able to communicate and interface with industrial Ethernet. Ethernet at the end of the day is Ethernet, but now we can work on systems that have time deterministic configurations. Because we're just calling a simple layer on a web page, we've got near real-time responses, and the reason for that is drivers quite often are designed for a number of use cases. So if you get hardware and you get the proprietary driver or the LXI IVI driver that belongs with that, quite often that driver will support multiple types of hardware. And so it can lead to slower responses because you have to drill through the driver to get to the data that you want. And so by directly accessing the instrument using REST, you reduce a lot of that response time. Also, because we're not using drivers, we have deterministic latency. It's achieved with buffering, but at least now when you acquire data, you get it in set packages and you know when you're going to be getting that. And also, if you're writing an application or you're developing a system for a customer, if you're creating that without drivers, you're using a driverless approach, then you don't need to supply your finalized software with the hardware manufacturer's drivers bundled in as well. You don't need to do any of that now. You can ignore bundling extra drivers, you just create the software. And to a degree, we offer low-level access using REST. So that means there's a lot more flexibility in programming the instruments. You're not locked to the driver's preset available commands. We've added a little bit more to this. So with our REST API, and it's a standard that we're pushing to be added to everything, what we have is something called discoverability. So you send a GET request to a directory within that web API, and it's going to return a list of all the implemented subdirectories and endpoints inside of it. So this means that you can discover every command possible that you can send to the instrument just with sending it a simple GET. So while you have a manual, and that's obviously important to know what it is that you want to do, by using this GET command, you know exactly what commands are available to be sent. So it works as, let's say, a reminder when you're writing your application, but it also ensures that you're not sending an invalid command to the instrument. So if we look below, we've got an image, and it's a Python control for one of our 16-channel strain gauge instruments. And we've created a RESTful HTTP module that you can import into Python that makes this even simpler. And what it does, it allows you to control the instrument. And as you can see here, we've given initialized or imported the driver, or should we say the module. We've initialized the instrument at IP address, 192.168.0.55, and we've called that instrument REST. And now from that point on, we type REST and dot on wait, and you'll get a list of the next available commands. So it really helps direct you to what it is that you need to be doing to control that instrument. And as an example of the advantages of why you would want RESTful HTTP driverless control, if you were to do the same commands or the same control in Python for Windows, and let's say you are using an LXI-based instrument and you've imported the IVI driver, so any programming application that you can import or call a DLL file, then you can control an LXI-based instrument. And the easiest way to do that, the highest level language, is to call those drivers in what's called a COM type interface. You either have IVIC or IVI COM, and COM is very high level and easy to understand, and it's pretty much a text-based control for your drivers. So in order to use that under Windows with Python, you have to import a module called COM types, and that allows you to create those calls to the driver. The problem comes that as you've written your application in Python, and Python's available on Linux and Windows and many other operating systems, if you write your code under Windows and then you try to port it across to Linux and use it, it's not going to work because Linux doesn't support COM calls, doesn't support the calling of a DLL file. And so now the application you wrote in Windows does not work in Linux. So therefore your code is not portable from operating system to operating system or platform to platform. And that is where driverless really comes in to its own. You can write your application under any operating system and use it in any other operating system. And so you can start to see how important controlling your instrument with a driverless approach, and RESTful HTTP is a great one over Ethernet, becomes very appealing. Now, while many open source Python modules exist for implementing HTTP and RESTful clients and all that side of things, we have published 2 libraries to make using our instruments via REST on Python even easier. And they give you a very much COM type look and feel to the programming, but they're not a requirement. If you wanted to just do it directly, you can. We've just added extras in to make it easy. But if you look at the 2 programming examples at the bottom of this slide, on the left you have the REST-based, RESTful HTTP-based control. And on the right, you have the IVI COM-based or COM-type control. And they are very, very similar in their approach. So if you've been used, or you're a system integrator, or you are a system integrator, and you've been used to writing applications in IVI COM or COM-type calls on the right, converting across to using a driverless approach is very simple. The commands are almost identical. The big difference is what's on the left will work under any operating system. Now, one thing to look at on here, and it comes when everything so far has been about configuring instruments, health monitoring, reporting back instruments status, and any preloaded configurations, etc. Part B of all of this is to actually acquire data from your instrument. And while via REST you can do that and capture individual slices of data as and when you want, if you're looking at high-speed data and streaming data from your test system back to process it, then REST and that side of things doesn't lend itself to high-speed data. And so there is a part B that goes with this. And to acquire data at high speed, there are a few options that you have. And the one that we've chosen and we'll talk about here is what's called VETA, which is, and VETA you may have heard of before. They usually develop hardware standards for PCs and things like this, but every so often a software standard comes out of them. And this time VETA Radio Transport, or VRT, is a standard that we've adopted, and it's VETA 49. It was developed as a method of transmitting data over radio. And this standard we've used as another driverless standard to get high-speed data out of instrumentation. So you require two parts, configuration via RESTful HTTP and data acquisition at high speed via VRT or VETA 49. If you're using Python or any other language like that, you simply install either the modules or you can configure it manually, but you require our little application, or let's say it's not even an application, a small module that we've created to convert the VRT data, the VETA 49 data that comes from the instrument, into a usable data that you can work with. And simply stated, the VETA 49 standard just defines a protocol standard that enables message interoperability between the equipment and multiple vendors so that everybody conforms to the same standard of transmitting data. So if we look at another example that I have here, we are simply using two things. We import our REST API and the VRT API, both driverless, so it doesn't matter what operating system you're working under or what processor type you're working under. You call the instrument, and this time not only do you call the instrument, and if it's a PXI system, the card and the slot number, but you also call a port number. So with VRT, we are streaming data to a UDP port, in this case 9901. So we configure the instrument via REST, we acquire data via VRT, and the two work together. If we take things one stage further and look at platform and processor independent programming, we come on to this thing that I keep mentioning, and that's Node-RED. And that's a little something that I just want to add to the end of this to explain what this can add to all of this. Node-RED was developed by IBM, but it's a community-driven, open-source, LAN-based programming environment. And the interesting thing is, it allows any API, any web page, any hardware that is connected to a local area network to be wired together, to be programmed to communicate. And the concept of that is very interesting. So in the same way that LabVIEW from NI became a success for quickly creating test and measurement applications, Node-RED uses a very similar block diagram and then front panel approach. So you have one web page, which is your block diagram, and a second web page, which is your front panel. And you can have multiple front panels off of one block diagram. So the way this works, and I've got an example at the bottom here, you literally run a drag and drop system. So you pull in a you give a command, as I have here, let's say a 10. You tell that to set the range, and you send it to the instrument by wiring these things together. On a separate web page, you can view your data and your configuration, and you can configure how this all looks, etc. But what it means is you don't need any programming experience. You just use our native nodes that we've created, or you can use Node-RED native nodes, and you can develop your test system without a driver, without any programming language or programming experience, and you can create controls, read back data, and display it as graphs, bar charts, gauges, anything like that via a web browser. And as I said, Node-RED is free, and it only requires a web browser as both your programming environment and your graphical data display. At the heart of Node-RED is JavaScript, but you don't need to be a Java programmer to be able to use it. Controlling VTI hardware, as I said, is done with no programming experience. And so long as you have a local area network, it doesn't even need to be connected to the internet, you just need a local area network for your test system. You can run some pretty simple initial configurations through to very complex test systems just with drag and drop and using the REST API to control everything and send and receive data via JSON. So I've got a simple setup here where you can get channel 1 range. So you just click on the box and you get a range, and it'll give you the result of what range your instrument is set to. Or you can tell it to put a range. So you say, I want it to be range 10, select 10, it puts that to channel 1 and it sets that channel to range scale 10, let's say 10 volts. And it really is a drag and drop system like this. These are all pre-configured. You simply give them a usable name that you understand and tell them what website address they're looking at or what instrument address they're looking at. And modifying those nodes is really quite simple. So channel 1 range number, host name, in this case, rather than IP address, we're using a host name, slot, if it's a PXIe based chassis or something like that, and then the path, which is quite simply the website address, and whether you want to put the data or get the data. So in this case, we want to call it back. So running this is going to get you a response to tell you what range channel 1 is set to. And pulling it all together and trying to understand what this all means. And the world has come a long, long way since the invention of machine code, as I think we've seen in here. And it's continuously accelerating in its development. And every step has always added more simplicity and greater speed. And all of this is happening while incorporating standards that enable greater compatibility between hardware. And it's going to continue to evolve. And as you develop your test system, the general message is try and use the most widely adopted standards applicable to your application. And if at all possible, use the newest programming methods that fall within that. And if you do that, it's going to ensure the longest life and avoid obsolescence for your test system. Things like Ethernet have been around since 1980, and they are not going anywhere soon. They're certainly here. And more standards are being built off the back of Ethernet. Such as we've just seen Node-RED, and certainly since the beginning, RESTful HTTP. And then there's that mindset change that while IoT was initially considered a gimmick, as just it's now undeniable that it's leading the way in new development. And the really interesting thing, interesting for sure, is that it's estimated that by the end of the decade, as many as 50 billion IoT devices will be online. That's massive. And IoT is now at the center of every technological advance in every industry imaginable. So let's all be part of that. Let's incorporate that into our test system. And that mind change comes in that rather than looking at it as your smartphone and accessing all the smart gadgets around your house, why can't it be a smart tablet or whatever it happens to be, and it's acquiring data and displaying you and giving you control of your test system within your factory or your lab or wherever it happens to be. And you can share that data with all your other facilities, and you can set it up so that you have access to just the data you require at the time you require it. And beyond that, because you are looking at a global system, then you can back up your data globally and share it globally real time if you need to. So I'll add a few more bits to that conclusion as well. So the REST API and Node-RED nodes really do make it easier to prototype and to a certain degree develop applications, and it connects the physical world to cloud applications. And that's what we're trying to do here, and that's the very definition of IoT. Driverless RESTful HTTP certainly helps accelerate the rollout of test and measurement applications, and it does that by flattening the architecture. What you're doing when I say flattening the architecture is you're missing out the middleman of having to use drivers and learning everything that goes with a particular manufacturer's driver. You're going straight to directly controlling the instrument via a globally accepted communications method. And as we've seen, flexibility of RESTful HTTP and the use of Ethernet certainly adds a lot longer, greater viability to your project test system investment. You're minimizing obsolescence by using the latest standards and the most common standards. So RESTful HTTP should be seen as a tool for making it easier to integrate data acquisition systems into a world dominated by IoT. And that includes smartphones and other portable devices that run OSs and other Windows and Linux-based devices. So RESTful HTTP is certainly a developer's best friend for customized test systems. And that kind of brings me to the end of where I wanted to be. I hope you all follow. And we'll look at some questions and answers.
Thank you, Nathan, for that presentation. It was fantastic, very clear, setting out very clearly some complex things there, which was great. And let's move on quickly. We've got about 10 minutes left, so we've got time for a few questions, which is great. So I'll dive straight in. Firstly, here's a question from Michael Lynch. Have you incorporated WebSockets for data streaming to user interfaces?
Yes, so we do use data sockets, and that is how we stream via our UDP port to usually port 9901, but it's configurable. So yes, we do incorporate WebSockets for streaming.
Perfect. A lot of the you mentioned several times about Node-RED, this the new programming language. Where did you find out about that yourself?
It's an interesting one. It actually came to me by one of our large aerospace customers who are actually looking to use it to deploy on one of their test systems that they could only ever get remote access to. So they had a large system that once set running, they weren't going to be able to get anywhere near it for a good month or more. And then they wanted a system that they could access and monitor everything remotely and make any changes as they go. And so it was that aerospace manufacturer that actually introduced me to Node-RED. But it was interesting at the time that was their application, and that was what they chose to do it. But yes, it came, like I say, it came from an aerospace manufacturer.
Fantastic. Well, that's highly relevant then. That's
Yes.
good to know. Right, the right industry, and yeah, I mean, it's fascinating, isn't it? How this sort of like everything is becoming, as you say, simpler and quicker to use. So like with these new languages, etc. Now, there's another message popped up there, and now I can't see where it's gone. So, but with Node-RED, the block diagram and programming page, can that be locked at all to stop users changing the code?
Yeah, good question. Yes, it can, and there's a couple of methods to do this. In fact, there's more than two, but the two main ones, because what you're looking at is a web page, you have the option to go and change it from HTTP to HTTPS, which then makes it secure. And from that point, you can then issue certificates to the people that you want to have access. Alternatively, and again, because it's a web page, it's perfectly possible to set it up with a username and a password so that you can password lock. your programming environment, as it were, the block diagram side of things. And you can do that on a certain number of levels. So you can grant different access rights to people as well, depending on their passcode that they use. So yes, you can lock the programming environment.
Useful indeed. I've got another question here from Brian Haggerty, who asks, have you created libraries that support BSON, binary JSON, for data exchange?
At the moment, we have them purely for instrument configuration and very basic data exchange, so taking one slice of data at a time. But it's certainly something that we are looking at.
Excellent. And we have just returning to the node red. Can you use that to deliver a turnkey software to a customer?
You can, and like all softwares, yes, you can. What you need to do is generally, if you're delivering a turnkey solution to a customer, it's going to be built with its own local area network incorporated into that test system. So you set your instruments up to be static IP addressed, and you set up your server PC to do the same, at which point you can develop your Node-RED application using those static IP addresses. And so when you deploy your test system, nothing changes. So yes, you can distribute test systems like that, and you just use static IP addresses, and everything continues working. You continue publishing and being subscriber, etc., to that test system.
It's fascinating. It's so useful, and you explain it so clearly there. It's been a fascinating hour. I think we have I think we've got an email address for you here. For anyone that joined late, this has been Nathan Henderson talking. He's Senior Applications Engineer with VTI Instruments. My name's Tom Stone. I'm Editorial Director for Aerospace Testing. And so just to finish there, there's Nathan's email address there. If anyone has any further questions, I'm sure he'd be very happy to answer them. You can contact him on the email address there. And this webinar will be available on demand afterwards, should you wish to return and rewatch any portions, or indeed share it with your colleagues. So I think that wraps up. Is there anything else you wanted to wrap up with there, Nathan?
No, that's everything, and thank you very much for giving me the time to talk about this.
Brilliant. It's been a great hour. So thank you, and hopefully see you again soon.
Perfect. Thank you.
Okay. Take care.